Hello. In the last lecture, we considered nonlinear regression models. And the first simple extension of the linear regression model to nonlinear regression model is using polynomials. It's pretty straightforward. Just choose how many terms you are going to include, and then just define new random variables as the squared x or cubic squared x or higher order terms of x. So, however, we typically we do not go more than fourth order. That's even so. Fourth order is used when you have a huge data set. In most cases, second order is enough. So it is true that linear model may not fit the data well. Then usually we consider the second order function, the quadratic function, but usually we do not go beyond it. So maybe at your level, unless you have super large or special cases, quadratic function should be enough. So we may consider a quadratic function of income, like income, and you define income squared. You may treat income squared as another regressor. And if you consider cubic function, you get two new random variables, income squared and income cubic squared. So this is the second regressor and this is the third regressor. So in this way, you may increase the number of regressors as much as you want. And then regression, once you define the new variable using the generate command, which we use in homework 4, I guess, then simply just include the new random variable in your regression. So you get this result, and your fitting line will be curved. Your trend line is now curved, and you you get a better fit. What's important here is so far implementation is not that difficult, but what you need to be more careful about is its interpretation. So previously, I said you can treat income squared as a new random variable, as another regressor. That is true in implementation. However, in interpretation, it does not work, because if income squared was another or not a different regressor, then usually we interpret this coefficient as, so 3.85 is the effect of income on the test score, given under the assumption that the other regressor is held fixed. However, that was possible if you think if this was a totally different regressor, but in this case it's not possible. You cannot hold this part fixed and change this part only. That was not possible. So interpretation should be changed. For example, when income changes from 5,000 to 6,000, obviously income is affected, and obviously income squared is also affected. So they are moving together all the time. Therefore, your interpretation has to consider the co-movement at the same time. It is like differentiation. So when you differentiate a cubic function, you have multiple terms. And another interesting point here is the effect, the slope, differs at different points. So in our graph, as you can see, the slope becomes flatter as income increases. I explained the intuition. So as you become richer, additional dollar means nothing. The value of additional dollar decreases. The marginal income, the utility from the marginal income diminishes. So we have that. And another problem here is it's a common problem in a quadratic function fitting. If you use quadratic function regression model, then you have to understand that quadratic function is always U-shaped or inverse U-shaped. That means if the quadratic term's coefficient is negative, then your function will be inverse U-shaped. That means at some point it will start to go down, right? It increases and then after the maximum it goes down. But however, in some examples like this, it is not natural or not intuitive. So it is counterintuitive to think about a negative slope. Higher income implies lower test score. Does not make much sense. But usually that kind of problem is coming from the range of the data. So the range of the data is from around 5 up to like 55. So in this range, the slope is like positive or near zero. Even if there is a slight drop here at the end, but we may think it is flat. The slope is zero. But if you go further, it will drop drastically. So then the interpretation doesn't make any sense. So you have to be careful. You should not you should not conclude that the effect of income turns negative after a certain point. It's not right because you are predicting out of the data range. And by the nature of a quadratic function, it cannot be right. It has to be negative at some point. So it's not. It's just a nature of the quadratic function. So, like for example, if you calculate the effect at $65,000 income, then it will be negative. And extending the same idea, you may consider cubic function. So, generate another variable. GEN is a abbreviation of generate. Generate average income 3 cubic term, which is average income times average income squared. So regress, test score on average income squared, average income cubic squared. And robust, R stands for robust standard error. So STATA has many abbreviations. Then you get this result. So you have coefficients for linear term, quadratic term, and cubic term. And I draw the fitting line by myself. You will get this kind of function. The difference here is it's cubic function. So quadratic function is always U-shaped. It goes down at some point. But cubic function looks like this. So it goes up and there is one bump and another bump and goes back up. So you can see that it goes up and there the slope changes and then changes again. So if you continue, it will go like this. It will increase like that. But we are not going outside of the data range. Outside of the data range is hard to interpret in our model. Anyhow, what you can see, by the way, here is that so having another term, including the cubic term, will improve your fitting, no matter what you are doing, always. However, does it make a significant difference? I don't think so. Quadratic fit is like this, and then the difference between linear and quadratic looks significant, but the difference between quadratic regression and cubic regression, I think they are pretty similar, and so I don't think their difference is significant. So that that is a typical question, and it is reflected in the p-value. So linear function is very significant. Linear term is very significant. P-value is very, very small, which means very, very significant statistically. And the quadratic term has a p-value of 0.01%. 0.1%, excuse me. 0.1% is p-value, which is still pretty good. However, the cubic term has a p-value of 4.9%. 4.9% is marginally significant at 5%. So it is still significant, but relative to the other guys, it's less significant. So yeah, it's not bad. And if you read the t-statistic, so linear term is very big, 7, and quadratic term is also very large, 3, but the cubic term is 1.98. Remember, the threshold is 1.96, so it's marginally significant. So cubic term is doing something. It's doing well, and and like we may then consider a formal test of the functional form. So let's think about a hypothesis test that my null hypothesis is linearity. So the effect of income on test score is linear, like this, which means the slope is constant everywhere. The effect of additional dollar is the same whatever the income is. However, again, the alternative hypothesis is, so if the null hypothesis is wrong, that means the regression would the data will be better fitted by quadratic or cubic function. So in our regression model, you can state the null hypothesis in this way. My null hypothesis is that the relationship is linear, so the quadratic term and the cubic term should have 0 coefficient. So the coefficients on the cubic and quadratic cubic terms must be 0. So only linear term is significant. Alternatively, versus the alternative hypothesis that at least one of these higher order coefficients is non-zero. If this is non-zero, that means the function must be at least quadratic, and if this is non-zero, the function must be at least cubic. And we learned how to implement a joint hypothesis test. So test this coefficient, right after running the regression, and then you get a p-value of 0 or f statistic of 37. Remember, if it's greater than 3 when you have 2 degrees of freedom, 3 is the threshold, so 37 is much higher than that. Or the p-value is 0.00%, which is super significant, like rejected at any significance level. So as a result, your null hypothesis is rejected, and we believe that it's the cubic function is better in our data. Okay, then summary. In summary, so estimation is nothing new. Just you define some new regressors, but interpretation is more complicated because they move together. So you have to be careful, and you should calculate the effect of the regressor on the outcome at different points. Different points will have different effects on the outcome. And you may also compare whether your polynomial function is better than a linear function or quadratic function using the test that I showed you like this. So you may test whether higher order coefficients are 0 or not. By doing this, you can choose which is better, like whether a linear function is best or quadratic or cubic. So that can be done by this procedure. Okay, and the next video, I'm going to explain a different nonlinear model, which is also very interesting. See you later.